Welcome back to ECE 442-542. This is section E of lecture 6.2, and this particular lecture is now dealing with generalized notation, the G bar that we've been talking about. When we pull all of the pole and zero factors from the controller and the plant, collect those into this generalized transfer function G bar, and isolate the gain K to put us in the standard form or standard structure for the root locus sketching. Here is our generalized notation via an example. Suppose that we have a plant, 1 over z, z minus 2. Hopefully you can now see that that plant is unstable. We have a controller that is k, z over z plus 1. So we have a 0 at the origin, we have a pole at minus 1, and we have a gain k. What we want to do then is collect the pole and zero factors from both the controller and the plant, put all of those together into this G bar, our generalized plant, and then have sitting out front the adjustable parameter K. This is now our standard root locus diagram notation. We've now pulled the adjustable parameter K out from all the other factors in the controller and the plant. This is now our generalized plant. We have now zero factors, and these are now the open loop zeros, and we have our pole factors, and those are the open loop poles of G bar. What we want to do now is, based on this particular example, sketch the root locus associated with this controller plant combination. And I think you can see almost immediately, I hope, that that factor in the numerator cancels the same factor or a similar factor in the denominator, and effectively then G bar becomes a two-pole generalized plant with one pole at minus 1 and one pole at 2. No finite zeros. We have two zeros at infinity. We now know what that diagram needs to look like. We know, based on the phase angle condition, that the real line segment between minus 1 and 2 has to belong to the root locus. The line segment between 2 and plus infinity does not belong to the root locus, so it's not read. The line segment between minus 1 and minus infinity is not belonging to the root locus, because if we look at the angles that those two poles make at those two outer line segments of the real axis, the angle will be 0 degrees. In between those two poles, the pole on the right contributes 180 degrees, the pole on the left contributes 0 degrees, and we'll have then the sum of those being 180 degrees. We can now use the magnitude condition. In this particular case, we know the structure, we know the root locus. It's now one branch starts at 2, the other branch starts at minus 1. They move towards each other. That's why the arrows are drawn in the way that they are drawn. They meet halfway between those two. We are a distance of 3 apart. So they meet 1.5 units away from where they started. That means that they are going to be hitting each other at a value of z equal to 1/2. We now want to know, how do we find the gains at these various locations? Because we can actually see that we will stabilize the system once we crank up the gain k to get us to the box. We can continue to keep the gain or the system stable as long as we keep the gain less than the gain required to get us to the triangle. We now want to know, how do we determine those gains? We have k g bar of z equaling 1. That's our magnitude condition. We can plug in what we know g bar is. G bar, and we're going to assume that k is positive, so we don't need to worry about the magnitude of k. K is positive. We now have the magnitude of the denominator, which the denominator was z plus 1 times z minus 2. But the magnitude of a product is the product of the magnitude, so we can actually look at the magnitude of the factor z plus 1 times the magnitude of the factor z minus 2, and that has to equal 1. We can now solve that for k, and we now can see how to adjust k to get us to these different locations. This is our formula to calculate the gain k. We simply plug in different values of z, and that will give us the values of k that we need to get us to the box and to get us to the triangle, if we can find those values. Now, to get us to the box, what's the value of z? Well, that value of z is right on the stability boundary. That's when z is equal to 1. The gain then, k, at the box is the product of the z plus 1 factor magnitude times the z minus 2 factor magnitude, and that's going to happen, or be that gain, when we evaluate the expression for the gain k at z equal to 1. So now we have 1 plus 1, that magnitude, times 1 minus 2's magnitude, or we have 2 times 1, or a value of 2 to get us to the box. That means that if we have this knob k that we can adjust from 0 to infinity, we need to get that knob turned up to at least 2 before we get this system to be closed loop stable. Now we need to figure out what's the gain to get us to that triangle. Can we find what that value of z is at the triangle? We know the real part. The real part is 1/2. Now we also know that that triangle is on the unit circle. We know it's a distance of 1 away. Now we have this right triangle, one side being 1/2, the hypotenuse being 1, and that now allows us to find the vertical distance, or the vertical side of that right triangle. If we now look at that triangle, we have 1/2 squared plus y squared is equal to 1. We're trying to find z delta. Now if we solve that for y squared, we have 1 minus 1/4, or that's now 3/4. So y is the square root of that, or it's the square root of 3 over 2. Z delta now is going to be plus j square root of 3 over 2. And the lower triangle is going to be 1/2 minus j square root of 3 over 2. So now we know z delta is 1/2 plus j square root of 3 over 2. We plug that in to our formula to compute the gain k. So we replace z in z plus 1 with 1/2 plus j square root of 3 over 2. We replace z in the expression z minus 2 with 1/2 plus j square root of 3 over 2 minus 2, and that now will give rise to a eventual gain k delta of 3. So our system now is stable if we crank up the gain k from 2 to 3, and that's from k box to K triangle. This particular example now, with using the generalized notation of our G bar, allowed us to use the magnitude condition to determine range or values of K that allow the closed loop system to remain stable. Just as a reminder, all root locus rules come from this condition, which is the closed loop pole condition, or the denominator of our closed loop transfer function, 1 plus k g bar of z equal to 0. We subtract 1 from both sides and we have k g bar is minus 1, but we can rewrite that complex number minus 1 as 1 at an angle of minus 180. With k being positive, the angle is not influenced by k, so now we have the phase angle condition, which is the angle of G bar. G bar is our generalized plant. That's all of our pole and zero factors from the plant and the controller. If a value of z belongs to the root locus, then it has to have an angle of minus 180 degrees at that location in the z-plane. We also know the magnitude condition. We know the magnitude of kg bar is equal to 1. That now, if we have a point z that we know is on the root locus, we can evaluate this equation to find k at that particular value of z, and that's how we can use the magnitude condition to find specific values of maybe an unknown k value or magnitude value. Suppose that somebody says, we have these 3 poles, 2 are complex conjugate, 1 is real, and we have a 0. We want to find what is the angle determined or created by that combination of poles and zeros at that location star in the complex z-plane. We now can start at each of those singularities, the poles and the 0, draw a line from that singularity to the star and determine the angle that that singularity makes with the positive real axis and that directed line segment to the star. For the rightmost pole, that angle is theta p1. For the upper pole, that angle is theta p sub 2. For the lower pole, it's theta p sub 3, and for the 0, it's theta of z. The angle then, or the phase of g bar of z, is going to be the sum of the zeros angles minus the sum of the pole angles, because the zeros are in the numerator, the poles are in the denominator. These combine in terms of their phases algebraically by adding the numerator angles and subtracting the denominator angles. The angle then of g bar when z is equal to the star is going to be theta of z minus theta p1 plus theta p2 plus theta p3. Now somebody might say, is star on the root locus? Well, if you can calculate that, or if you can get out your protractor and actually measure those angles, if g bar of z at the star is equal to minus 180, we know that that point, star, is on the root locus. If, however, the angle, theta z minus the sum of those 3 pole angles, is not equal to minus 180, then we know that that particular location, star, does not belong on the root locus.